Now in this video I would like to talk about the vorticity and rotationality. These are the properties of our flow field that we utilize to characterize the flow field. Now in order to determine the vorticity and rotationality, we need another important property called angular velocity. So in the context of angular velocity, I will derive the equation for these and subsequently show you how we can determine the vorticity and rotationality of our flow field. Now in order to derive the equation for vorticity, I would like to introduce the concept of angular velocity, and for that purpose consider this analysis. Consider this small rectangular element of fluid at some instant of time t in the flow field. So that is my rectangular element, and these are my velocities in the x and y direction, u velocity and v velocity at point, for example, call it C, this point call it A, and this I'm calling it B, point B. So the change in this velocity, v velocity for example, with respect to x direction is indicated by this change, and similarly the u component in the y direction is indicated by this expression. Now I would like to go after some period of time what happened to that element. That this element has undergone to some deformation, and at some time t plus delta t, here is the deformed geometry of that fluid element. So now here make sure that again we have the del x and del y, the dimensions of this element, but it has been little bit contracted and rotated. So those rotations are indicated by these angles. So delta alpha 1 is the rotation in the clockwise direction, and delta alpha 2 is the rotation in the counterclockwise direction. So these rotation, in addition to the change in the velocity that I have already mentioned here, will help me determine the displacements, the Lx and Ly in the x and y direction, and subsequently those I will utilize to determine the change in the angular velocity of the line CA and CB. So make sure that line CA is now CA prime changed, and CB is CB prime. So it means that there is a change occur, rotated. CA has been rotated to CA prime, and CB has been rotated to CB prime. So there is a change in angle that will help me determine the angular velocity of these two lines, and that will be determined utilizing the Lx and Ly. Now I have determined the displacements in the x direction based on the definition of velocity. The velocity multiplied by the time will provide me that distance Lx, and similarly the change in velocity multiplied by the time will provide me the displacement in the y direction. Let's call it 1 and 2 equation. Now in addition to that, I can also determine the Lx and Ly from the geometry of deformation at time t plus dt. For example, if you go and look back at the figure, using the definition of arc length, which is radius multiplied by the included angle, I can easily write that Lx equal to this, let's call it number 3, and Ly equal to this, which is number. This negative sign is because the vertical side of that element, fluid element, is rotated towards the clockwise direction, and that's why the angle is negative, and that's why I put the negative sign in that direction. Now if I go and equate equation 1 with 3 and 2 with 4, I can easily write down the values for my angles, change in angle, that is delta alpha 1, as if it will be equal to this, and similarly for delta alpha 2, I can easily write down this. So using the concept of calculus and limit, I can write down the change in angle divided by the time, which is my angular velocity. Okay, so I can write down my angular velocity for line CB. Okay, this is for my line CB, and this is for my line CA, the angular velocity for that line. Now by definition, the total angular velocity of the fluid element is the average of the angular velocities of line CB and CA. So I will go and add these two, CB and CA, together to determine the total angular velocity of the element. So which is nothing but this equation indicated by omega, this symbol omega z. Make sure that it is the z component. Okay, z component of angular velocity. So omega is actually a vector. Now subsequently, for a three-dimensional flow field, the other components of angular velocity can be determined in the similar way. So I can go and combine all of them and finally write down this equation to indicate that this is my I component, this is my j component, and this is my k component. That k component that I have determined and shown you. So you can repeat that for finding out the I component and j component, the similar procedure. Now finally, in the vector form, this omega, the angular velocity, can be expressed like this equation, and after that I can define the vorticity, which is twice of my angular velocity. So vorticity I indicate with this symbol, I will call it xi, and will make it twice of omega. So this is my vorticity of the flow field. So if I give you a vector velocity field, and ask you to determine the vorticity, you just go and take the cross product of that del operator of that velocity vector to determine the vorticity. This is called the curl. The cross product of del with a vector is called the curl of that vector. Now moreover, I can define my irrotational flow. So irrotational flow, when my vorticity is 0, that is this is 0, then this condition is 0, then my flow field will be an irrotational flow field.